Hello, my name is Eric Turman, and I am studying computational fluid dynamics under Dr. Wayne Strasser. I'm a member of the Fluid Research Group out of Liberty University, and I will be discussing merging controls technology with CFD for the purpose of responsive computing. CFD is a powerful tool that can result in great breakthroughs in research. Gathering useful data from a CFD model requires the model to be quite complex to capture all the different intricacies of the problem that you are trying to simulate. CFD models can result in unrealistic data when not following proper setup procedures, and that can just result in wasted time and data that is not matching realistic situations. To be able to develop an accurate model, you need, at minimum, a computationally expensive turbulence model to capture all of the flow characteristics. You must reach grid independence, that way the mesh is not interfering with your results. And if you're running a transient study, you must find time step independence so that you're finding accurate results within a given time step of the flow. My research is proposing that through coupling a proportional integral derivative controller or PID controller to a CFD model, one is able to circumvent the challenges that come with complex modeling in CFD while maintaining the ability to produce reliable data. PID controlled models reduce the unknowns when completing a run, as a model can be instructed to automatically reduce error without any user input. This function creates the opportunity to instruct a model to make changes based on experimental data so as to ensure the calculations have a realistic baseline to use when completing their simulations. It also creates an opportunity to instruct a model to focus on key aspects of a study, such as a material property, specific boundary condition, or output variable from a CFD run. The following equation is used within the controller to compute the impact that the controller will make on the system it is operating in. It is looking for data from the current error from the previous time step, and error from 2 time steps ago in order to make a calculation. When testing the algorithm on a model, that user will alter the gain, integral, and derivative constants based on the feedback from the model. The gain will account for linear corrections to the error, the integral will address how long the error has been in place, and the derivative will affect how quickly the values approach and depart from the set point. The diagram below is a visual representation of how the controller functions. The set point is fed into the controller along with the data from the previous action to make the next decision. This process continues at a specified sampling time in order to make informed actions to control the system. The primary goal of this study was to couple a PID controller with a turbulence model to make a more computationally efficient model, yet producing highly accurate results. To start the study, a proof of concept model was developed using a 1.5 meter long pipe with a 1-inch diameter and flowing water through this. Reynolds number 50,000 was used to induce turbulence from the inlet. The current testing procedure just coupled a controller to an SST model for this study. The controller measured the pressure on the inlet and changed the turbulent viscosity value to alter the pressure drop through the pipe. This simple proof of concept for tuning turbulence constants will then be able to be applied to more complex models in the future. As the plot shows, the turbulent viscosity was effectively altered through a series of calculations completed by the controller. The controller gathers data for a determined amount of time and then performs a calculation, resulting in the step response seen in the plot for both cases run. You can see that run 1 was run with a set point of 5,000 kilopascals, and run 2 was run with a set point of 6,000 kilopascals to test the robustness of the controller and to ensure that it was able to meet 2 different set points when different conditions were presented to it. Due to the simplicity of the model, the controller finds a viscosity value which satisfies the set point. It doesn't require to make any more significant changes right at 1.5 seconds, as can be seen in the plot. The following pressure drop plot coincides with the previous plot showing viscosity changing along the flow time of the pipe. We can see that a baseline model was run with no controller, resulting in an 8 kilopascal pressure drop through the length of the pipe. Then, as run 1 and 2 both show, they reach their set point of 5,000 and 6,000 kilopascals respectively. This shows the ability of the controller to reach its set point through a certain amount of flow time based on controlled actions made by the controller to change the turbulent viscosity. To further expand on the usefulness of PID control within CFD models, a low-density polyethylene autoclave reactor was modeled within CFD. This type of reactor is prone to thermal runaway, so the CFD model had to reflect this scenario. Heat within the model is generated from kinetic energy due to the stir shaft and unstable multi-step radical chemistry from the polymerization process. The goal of the model was to understand what leads to these thermal runaway events and to reduce them through improving the process. The model had an iterative approach in increasing complexity to better understand the material properties at the outset or at the outlet of the reactor and to be able to predict what's going to be the material properties of the polymer based on operating conditions. 5 independent PID controllers were instituted within the model to alter the inflow of catalyst and to reduce the reaction rates and heat generation by varying the mass flow rate into the reactor. This study involved implementing data from actual reactors to be used as a set point for each controller. Within the CFD model, thermocouples were modeled to replicate the actual reactor. So each thermocouple would be located within the CFD model where they're actually located in the reactor. Temperature data from the controllers was taken at each thermocouple geometry, and the data was sent to the controller after computing a moving time average to reduce noisy data being sent to the controller and making too rapid of control decisions based on unreliable data. Each controller had to be independently programmed, meaning the proportional, integral, and derivative constants for each controller were tuned based on environmental conditions, convective timescales, and the proximity of the thermocouple to catalyst ports. The industrial scale reactor is split up into 4 separate zones, with each zone being separated by a baffle. There are 4 reactant feeds which feed into Zone 1, and then the 5 catalyst feeds are injected into Zone 1, 3, and 4. This replicates the actual process within the reactor used in the plant, and then the finished polymer exits out of the bottom of the reactor. Each of the 5 independent controllers have to be able to respond to upset conditions within the reactor. The material has a residence time of several minutes within each zone, especially with Zone 1 being the largest, followed by Zone 2, 3, and then 4. These conditions, which are often realistic within the plant, can see the temperature rise or fall drastically depending on different hotspots located throughout the reactor. By testing the controller's ability to respond to these either hot or cold temperatures in different zones and their ability to reach their set point, able to validate the robustness of each controller working in unison to control the temperature of the reactor. All 5 controllers can be seen here responding to an upset condition set at time equals 0 and eventually dialing in on the set point, which is 0 here on the y-axis. Since each of the 5 controllers experience such different environmental conditions, convective timescales, and are at varying locations throughout the reactor, independent tuning is required for each one, basing changes on the integral, derivative, and proportional gains within the controller. As you can see on the plot, this normalized controller inputs show the response in 10 seconds of flow time for all 5 controllers. Controller 4 is highly turbulent, which is in reference to the turbulent length scales on the order of the thermocouple length scale, and this region is extremely turbulent as can be seen on the next slide animation. The following animation shows thermocouple 10 within the reactor. This thermocouple is used to gather data for controller number 4 so that it can base its decisions on how to alter the mass flow rate of the catalyst into zone 3 of the reactor. As can be seen here, the turbulent flow around this involves creating a high temperature gradient throughout the length of the thermocouple, and this results in a very different moving time average across just several milliseconds of flow time. Because of this, the controller has to respond quite rapidly and with much more gain than the other 4 controllers within the model. The 5 controllers within the reactor were able to respond to the changing conditions within the reactor and to maintain stable temperatures throughout the 4 zones. It proved beneficial to couple controllers with the ongoing development of the model, as this allowed for the model to respond to new conditions and new changes imposed on the model, and then assist it in reaching quasi-steady state while running. The entire model became much more robust through its ability to automatically reduce the error at the thermocouples due to the action of the controllers. This eliminates the need for constant input from the user and allows for a much smoother process when running the model and experimenting with different changes to the reactor. As mentioned, this is initial work for merging controls technology with CFD for responsive computing. The scope of this research continues to develop and look for more avenues where PID can be applied to CFD models. Current plans involve adapting a controller used on the pipe flow model to a hydrofoil geometry. The hydrofoil study was conducted with a 12 million element mesh using the RANS turbulence model. As expected, this result was very computationally expensive, but was able to match experimental data and validate the CFD used to run it. The goal will be to use a PID controller to tune a turbulence model and use a 1 million element mesh to arrive at the exact same results. This will be able to prove that PID controller can develop a new approach for affecting models and resulting in accurate information. The eventual goal of this project within the fluid group is to transition from PID controllers into machine learning algorithms coupled with CFD models, specifically using rewards-based functions to control models and result in better computing methods, both in terms of computational cost and time. Thank you very much for listening to my talk.